This is a brief introduction to linear regression. My name is Alden Gross. I am faculty in the Department of Epidemiology at the Johns Hopkins Bloomberg School of Public Health. So what is linear regression? Linear regression is a statistical method for describing the relationship between an outcome variable, we're going to call it y, and this outcome variable is continuously distributed, and some explanatory or predictor variables. There can be several of those. We're going to call them X collectively. Linear regression was originally used in the early 1800s in astronomy to predict planetary movements, but since then it has become a cornerstone of statistical analysis in all sorts of fields, including health and medicine, of which most of us are conduct research in. So linear regression, it's this statistical method for describing the relationship between an outcome variable y and some explanatory or predictor variables x. And you can visualize linear regression with a scatter plot between two continuous variables. On the y-axis here, or the vertical axis, I'm showing an outcome variable, writing score. And on the x-axis, or the horizontal axis, is a reading score. And this is a data set of about 200 observations. So we have writing scores and reading scores on 200 people. And this is a scatter plot of writing scores against reading scores. Now let's say that we want to describe the correlation, the relationship. We could calculate a basic correlation, which is similar to regression, but it's very basic, and it does not allow, a correlation does not allow for more flexibility in modeling and exploration of relationships. It's not as flexible as linear regression is. So let's talk a little bit more about linear regression. Linear regression is really about fitting a line through observed data to describe the relationship between x's and a y variable, an outcome variable. There can be multiple explanatory x variables, which you can call explanatory variables or covariates, which we'll cover shortly. So, if you think about the basic equation that we all learned in algebra, we can describe the rise over the run, or y equals mx plus b. B is the intercept, which is the level of y when x is equal to 0. And here, the level of y when x is equal to 0, the level of y as drawn in this graph looks to be about 39. So that would be the intercept. The trick is the x-axis does not go to 0. And so because of this, I think the intercept for the reading score would be, the intercept for the writing score would be an extrapolation. It would probably be close to, it would be close to 0, given, or maybe closer to 20, probably, given the reading score. M here is the slope. It's the difference in y per unit difference in x. It's useful to note here that the covariates in linear regression do not need to be continuous, the x variables or the explanatory variables. It is just easy to graphically explain when there is a continuous covariate graphed against a continuous outcome variable. There are 3 broad uses for linear regression. The first use is to quantify associations. For example, what is the relationship between smoking and cognitive performance? Cognitive performance would be, excuse me, your continuously distributed outcome, and we would say we would regress cognitive performance on smoking status, which may be represented as a binary variable or as a continuous variable such as pack years or something like that. A second use of regression is to predict or forecast a future event, such as a diagnosis. So for example, what background characteristics may predict future BMI levels, body mass index. A third use of linear regression is to explain variation in an outcome. So for example, we may ask how much variation in cognitive performance, the Y, is explained by demographic variables. So here's a general equation for simple linear regression described in words. Here, simple means just one explanatory variable or covariate. So the expected Y is a function of an intercept or beta naught, and the predictor variable, and the relationship of the predictor variable with the expected Y is encapsulated by a parameter beta 1. This is the same equation as Y equals B plus MX that we described earlier. It's the rise over the run. The goal of linear regression is to estimate the expected or average value of Y. So here, beta naught is the expected or average value of Y when X equals 0. We typically call this the intercept or the constant term. Beta 1 is the slope term. It's the expected or average difference in Y per unit difference in X. The parameters beta naught and beta 1 need to be calculated from data. And these are calculated by choosing values for beta naught and beta 1 that describe the relationship between the X and the Y. And your computer program will choose these values for beta naught and beta 1. This is what the your statistical software will do. So how does linear regression arrive at the best solution? This is done via least squares estimation. And essentially least squares estimation means we minimize the distance, the vertical distance between each point, each observation, and the regression line here. So here I've shown the regression line that I described earlier, and each point has a vertical distance from that line. So for example, you see a point here just below the line, and I've drawn a red line up to the regression line. This describes the residual between this particular point and the regression line. So what least squares estimation does in linear regression is it tries to find the line, the fitted line that minimizes basically the squared sum of all of these residuals between each point and the regression line. Here's a regression of writing ability. Actually, it's simply a regression of writing ability on nothing. So this is an example of a linear regression output in Stata. Here we're regressing writing ability on nothing at all. So let's use this to go over some of the key characteristics on this slide. Starting at the top right, the sample size off of which this regression is based is 200 people. The F-test is a global test, which is chi-squared distributed, of whether the covariates in the model altogether, of which there are none here in this example, but it's a test of whether all the covariates explain a statistically significant amount of the variation. Here the F-test is 0, and it's not statistically significant, obviously. The R-squared describes the proportion of variability in the outcome Y, which here is writing ability, that is explained by all the covariates. Here, again, the R-squared is 0 because there are no covariates. The root MSE stands for the root mean squared error. And if you can remember from the previous slide, that red vertical residual line. So for every point, the difference between the point and the line, that difference gets squared, and all of those squareds get summed, and we take the average. This is the mean squared error, and we take the square root of that. The root MSE is not generally interpreted because it's not scaled in a common way across different outcomes. But you could interpret it if you are running multiple or several linear regressions on the same outcome, if you preferred. Coming down to the body of results, the coefficient here, the only coefficient in this model is the beta naught term. There is no beta 1 because there is no slope. So if we were to graph this regression line, it would literally be a horizontal line on your graph at y equals b, from y equals mx plus b. Here, y equals 52.775. It's a horizontal line. The standard error describes the calculated standard error of this coefficient. Now, if you were to take the coefficient and divide it by the standard error, you would get the t statistic. And the t statistic describes a measure of association, the statistical significance of the association. Here, this t statistic for which a p-value is provided is testing the null hypothesis that this intercept term is equal to 0. And obviously 52.775 is much different than 0. And for this parameter, as well as all other parameters, we provide your statistical output provides a 95% confidence interval. So a lower bound and an upper bound. I'll note there's a table of the sum of squares and degrees of freedom for the model and for the residual. I'm not going to go over these values here. These values, ultimately, if you really wanted to, it's possible to calculate a linear regression by hand without the use of a computer. And these statistics help you do that. Unfortunately, we do not have time to go over them right now, but I wanted to point out to you, if I just take so I've regressed writing ability on nothing. If I summarize the writing variable, I see that I have 200 observations for writing. The average writing score is 52.775. That matches the constant term. Because we have regressed writing ability on nothing, the linear regression output returns an intercept or beta naught term that has a value equal to the sample mean of the outcome variable, which is writing. In this case, here we add a covariate, which is reading ability, to predict writing ability. Note here, there's now a statistically significant f-test, which is a chi-squared distributed variable. This means that reading ability is related to writing ability. The r-squared is 0.356, so that means that reading ability alone, as the only predictor in this regression, explains 35.6% of the variability in the writing outcome. There is now a beta 1 term, which is the slope, and that's interpreted on the slide. This beta 1 represents the mean difference in y per unit difference in x. So this means that there's a 0.55 point increase in writing ability per 1 unit difference in the reading score. And again, the beta naught intercept has the same interpretation, but the value has changed. So the intercept is the mean value of writing ability when all the variables in the model have a value of 0. So if you'll go back, let me go back quickly to my regression line up here. Note that when the reading score is 0 on this x-axis, I have to extrapolate and draw a line further, and let me annotate here to show you what I'm doing. So this means that for a reading score, once the reading score hits 0, the writing score on average, according to this regression, will be approximately 23, I believe, from the regression output. 23.95, so close to 24. Going back to the 3 broad uses of linear regression, if I were interested in associations, I would mostly be interested in the beta coefficients of various predictors. So, and I can adjust for confounding variables or additional variables. If I were interested in prediction here or forecasting, I would focus really on the R² value more so than any particular beta coefficient, or perhaps the f-test for blocks of various variables, such as demographic variables, health variables, or sets of family history variables, or variables from your medical chart, etc. There are other statistics to calculate for forecasting, which we will not cover here in this brief example. Similarly, if I were interested in explaining variation in an outcome, here the 3rd use of linear regression, I would also focus on the R² value. Note again that the outcome should be continuously distributed and optimally normally distributed. Here, here I'm showing a linear regression with multiple predictor variables. So this is multiple linear regression, which is different from simple linear regression, which had only one covariate. In multiple linear regression, you can have any number of variables. Here, the slope is still interpretable as the mean difference in writing ability per difference in reading ability, adjusting for all of the variables in the model. So note that this reading ability coefficient has changed. It's gotten closer to 0, or it's attenuated. We still have a standard error for this coefficient, but we can still divide the coefficient by the standard error, and that t-statistic is 1.92. And the p-value associated with that is 0.056. Note that previously our R² with the simple linear regression of writing ability on reading was 0.356, whereas in this example, the R² is 0.60. So the addition of all these additional covariates has almost doubled the R². So we're explaining a lot more variability in our writing outcome. It's very important to assess model fit of your linear regression model. And there are 4 points that I want to make here. The first thing to do is to always explore your data carefully and understand every variable that you put into that model. Understand the distribution, understand what each variable means, understand the range and whether there are outliers. This is because these observations could come up as issues in your regression as you assess fit. So how do we assess fit? So remember that red vertical line, the residuals between each observation and the regression lines. We can ask our statistical program, such as Stata, to calculate standardized residuals, and a histogram of these standardized residuals, as shown in the upper right, should be normally distributed about a mean of 0. Another thing we can do is to plot a scatter plot of residuals versus X variables, such as the second graph down here. And this should look like random scatter, because conditioning on the X variable, there should be no relationship between there should be no relationship between the residuals and the X variable. If there is a pattern, then that could suggest some nonlinearity, or that could suggest a confounder that you need to add into your regression. And next, you want to look at a scatter plot of residuals versus fitted values for Y's, and that should also look like random scatter. And finally, it's useful to assess leverage and influence of outlying predictor values. We will cover that in the demonstration portion of this section. When should we use, extensions of linear regression? There are lots of advanced uses for linear regression that you can look into on your own time later on. For example, we can explore nonlinear relationships between X's and Y's by including quadratic terms or spline terms. We can assess interactions between two or more X variables. For example, say that we're looking at the relationship between smoking and continuous cognitive performance. We can ask, does the relationship between smoking and cognitive performance differ by sex, for example? When should we use linear regression? Well, first, you have to have a regression. You have to have a question of interest. And we'll estimate coefficients by running a linear regression on data. And this is the process of using evidence, which is data, to address a scientific question of interest. You use linear regression when you have a continuously distributed outcome variable, and if you have one or several explanatory variables or covariates, the X's. It's important to be aware of sample size. A useful rule of thumb, which is not, you know, the absolute truth, the absolute to be taken as an absolute, but a rule of thumb is to have at least 10 observations per explanatory variable in your data set. More observations per explanatory variable is better, and I advise you conduct power analyses to get a more detailed answer. When not to use linear regression. If you have a non-continuous outcome variable, such as a binary variable like disease classification, or a time to event variable. There are other types of regression, namely logistic regression and survival analysis, that will be covered in other sections of this workshop. If you have a highly skewed outcome variable, then you can still use linear regression, but you may want to consider a transformation such as log transformation or Windsorization, wherein we pull in extreme values of that Y variable, because otherwise we may have problems with the fit of the model. And if you have a very small sample size, then linear regression involves lots of assumptions. That's why it's so important to evaluate the fit of the model. So if you have a very small sample size, those large sample assumptions may not be met. If you're interested in more details, I'm talking about assumptions like such as that variables are independently and identically distributed, and the central limit theorem. So if you have, say, fewer than 10 observations per explanatory variable, consider other statistical approaches. Thank you.